you see molecules like this, but this is kind of fluorescing background that you have to take out to be able to super resolve signals. And so this you use this in some sort of way so that you can go from here to highly resolved molecules like this. Okay, so maybe we should bring the back light and then conclude, because I have an hour and 30 minutes, an hour and 25 minutes I'm talking. So what I've shown in this lecture is that we can super resolve signals by convex programming. In compressive sensing, stability is built in the random sensing mechanism. In super resolution, it is not. And you're going to have to assume something else to be able to trust your results. In particular, that the events are separate. Thank you very much.
Now is the Q&A time. Is there any questions?
Thank you, Professor. Okay, my name is Woody, and I have a question. To my understanding, that super resolution compared with the compressive sensing. The compressive sensing is to randomly sample the signal, and the super resolution is to predict the higher frequency from the low frequency. And my question is, if now we have the signal, original signal is mainly composed of the high frequency part. If we use the super resolution to predict, because we have fewer information of the lower frequency, is it still proper to utilize the super resolution?
No, I mean no, absolutely not. I mean you have this kind of signal to noise ratio issues I've alluded to, which is that if you have a signal which is very high frequency and you just see the low frequency part, in the low frequencies what you see, I mean basically the measurement process will destroy the signal, right? And so that's kind of why you cannot do it. That's why I've been focusing on these spikes, because these spikes, they have both low and, the spectrum of a spike is flat. It has a lot of high frequency component, but it also has low frequency components, because the spectrum of a spike is flat. And so when I make measurement about a spike, unfortunately, I see quite a bit of its spectrum, and I see enough to be able to extrapolate it. But if the signal is, I don't know, a high frequency sinusoids, and you make low frequency data, you'll see zero, and there's no way you can recover it. I can only do it because my spikes have both low and high frequency components. Now, I want to go back to your question, because your question is very important, and I think it alludes to what I talked about before, the lack of stability. Because if you allow me to make any signal by violating this kind of minimum separation condition, then what I can do is I can do something like this. I can make a signal which looks something like this, which looks like a very high frequency sinusoid. Right? If I can bunch up together spikes, then all of a sudden I can make a very high, I can arrange the amplitude so that it draws a very high frequency sinusoid. And then when I measure it, it's gone. And that's why I need the separation condition.
Thank you.
In a model, do you need sparse resolution?
Excuse me?
The number of, so if you model molecule as a data, it's the sparsity required.
Of course, yeah.
And it's related to the measurement.
Yeah, I mean, at the end of the day, I'm going to get 1,000 coefficients, and I cannot recover more than 1,000 events. In fact, I cannot recover more than 500 events because, I need two measurements at least to recover location and amplitude. So I need sparsity. Right? I cannot do without it. I mean, I need structure of some form. The structure I use in this talk is sparsity. There might be other things we might want to do. But yes, you need sparsity. Otherwise, okay.
Excuse me, I know since the function of needs sparsity, but if the signal itself needs sparsity, otherwise we can resolution version of the signal.
Can I have a signal which does what exactly?
I have a signal,
Yeah.
and it is not sparse,
It is not sparse.
but it is sparse to a certain region which you are known. And can we recover it from boundaries?
I see. I think there are things that are possible, but it's a new subject for me, and I prefer not to say things that I'm not completely controlling at the moment. But I think it's a very interesting, question you're asking. If I understand the question correctly, is maybe there are pieces of the signal which are sparse and pieces that are not sparse. Can you actually recover some sparse of the signal and maybe give up on others? Is that your question?
You say that the data model is sparse with respect to condition.
Oh, sorry. Oh, yeah, like maybe not in the time domain, but sparse in a different domain. That's what you're asking. Yeah, I think that's very interesting, and I think it's possible. You're going to need a notion of incoherency. So, yes. Obviously, here I cannot recover from low frequency data sparse signals in Fourier space. Because if you give me one sinusoid which is at high frequency, well, I'm going to see y equals 0, and I can't say anything. So, as long as you're sparse in something that looks like time, you're going to be fine. So you could be sparse in wavelet because they like time-like elements and so on. That's going to be perfectly fine. In fact, the extension I've shown where you could be actually piecewise constant, piecewise broken long, piecewise polynomial, this goes in this direction. And sparsity does not have to be like a bunch of deltas. It can be different.
So far you are doing the super resolution in spatial domain. I'm curious, can this approach to increase the temporal resolution? Usually camera is 30 frames per second. Can this approach be the high-speed photographic? Maybe one second, 1,000 frames, something like that.
Well, I mean, what you need is what you need is a good model. And you need a good sparse model. And if you have it, I don't see why not. But you need a good model. And in this application that you're mentioning, I have not thought about it, so I don't know what would a good model be. But if you have a good model, yeah, sure, things are definitely possible.
I have two questions. The first is, in computational photography, when we say super resolution, we mean we have a high resolution scene, and we have many low resolution observations of the scene, and we register the low resolution to get a high resolution. And is that different from your scenario?
Yes.
And the second question is, in the molecule case, the high resolution is just, in my point of view, it's just some dots on the black background. So we just need to know the position of the molecules, and I think you don't have to do so many things. You have just you have place the dot in the black background.
I agree with that. I agree with that. But you see, placing the dot in the background can be something that looks like this. Where are the dots?
I would say it's in the peak.
Yeah, but there are
highest peak.
There are 6 others.
I see.
Okay, so this looks like this. I mean, what you see is truly like this. Right? So, yes, I agree with you. There's probably a dot here. Is that the only dot there is? There are like 6 others. And they're not where, the peaks seem to be, by the way. So, I agree with you that it's, and I'm glad you asked this question. I'm going to start with your second question, because that's what people do at the moment. And the reason they came to see us, I'm happy to take criticism, by the way, because, it's something I'm starting, so if I can learn from you, it's a good thing. The chemists, here's what they do. I promise I will explain the algorithm. They do what you would do after stats 2 or stats 101. They say, first of all, these kernels are too complicated. We're going to simplify them. We're going to assume that it's Gaussian. Okay? assume it's Gaussian. So what they say is, well, you know, my microscope is really giving me, you know, if it was had clean data, it would give me a Gaussian curve like this. And all I need to know is it's exactly your point. It's like, where is the center? So it's a parametric estimation problem. Okay? All right. Now you have noise. So you don't get to see this. Right? So you're going to do kind of what they call match filters, where they're going to shift this Gaussian in such a way that you have the largest correlation. And that's what they do. Okay? That is the algorithm. I've described the algorithm right there. But to make it work, they cannot have a point source right here. And that's why they want things that are very separated so that they can actually do their match filters. Okay? And so when the algorithm, you know, you collect the data and you've got like high density like this, it's not clear what you should do. Like how many molecules are there? Like you don't even know. Right? So how many Gaussians are you going to fit? You don't even know. And so when the algorithm, and I'm not saying that they do the right thing, they say this we can process and they throw it away. And that's why in their experiment, and you can read it, and I'm discussing things that are in nature and science now, right? That's why they can only image very few molecules at a time because their data processing step will reject high density. Because high density, they say, we cannot do it. Okay? And so what it forces them to do is to actually create many, many frames. It takes a long time because if I could image 100,000 molecules simultaneously, I would be done within a few minutes. But let's say, because I cannot deal with high density, I can image only, I need 100 molecules per frame. Then what takes 10 minutes takes a few days. Okay? So now, maybe you could say, well, you know, when I have several molecules, they're kind of close to each other, all these Gaussians get bunched up, you can still, I can say, well, I'm going to do some EM stuff and do well. And maybe you could. You would have to know how many molecules there are. You know, what if there's a very bright molecule and next to it there's a tiny one? It would appear to you that there's not just only one. But in fact, there's not only one, there are two. So how would you do it? So this is a very good question. I'm not saying this is the right answer. This is an answer. At the moment they do what you suggest. They say, we're going to remove lots of parts of the image where there are two things are too clustered together. We cannot process it. We cannot run multiple Gaussians when we don't fit multiple Gaussians. We don't know how many we have at a single location. Let's throw this away. And let's just focus on the area where we're sure that there's one molecule. The downside is that it takes an enormous amount of time. And by the way, it's done by hand. This kind of segmentation, whether there are several or one, because there's human intervention in these things. This is completely automatic. So this chemist is happy because he says, I can, with this kind of simple algorithm, I can improve the workflow by orders of magnitude. It's automated, and then I can have high density. And when we compare the performance of algorithms at low density in a regime in which they work well, we already see improvements, which I'm not sure I understand, because I would imagine that a parametric method is better than what we do. But here is very low density, so molecules are really far apart now. So their algorithm will not reject. But already, like, this is their accuracy, this is their accuracy. This is like in nanometers. So we have like 16 nanometer of accuracy, we have 24. And so we're already better. And then we increase the density and we kind of don't lose too much accuracy. Or for them, it's becoming a disaster because their algorithm gets confused. So, I agree with you. It's a very good point. Maybe there are other methods. This is one of them. Your first question, yeah, super resolution means different things to different people. And to computational photographers, it means something what you just said. But if you open Wikipedia, so after the lecture, you go to Wikipedia and you type super resolution. It will be this.
I thought that part of the question is to ask you where the concept you introduced here could apply to scientific.
I don't know, I need good models again. And I've not studied enough computer vision to have a good model. So I don't know. I don't want to say too much. Maybe, maybe not. I don't know. See, I cannot do stuff without models.
Yeah, thank you for the excellent talk. I guess in today's talk you mentioned about compressed sensing, also super resolution, right? But to me, I'm a beginner in this field, so I think compressed sensing is to solve the undersample problem.
Yes.
And for super resolution will help to solve the relay resolution. Right.
Yes.
So
There are two instances of undersample.
So one is in time domain, the other is the spatial domain. So
now they're both in the same domain.
same domain.
They are both in the same domain. There are two undersample problems. The problem is that in compressed sensing, I can sample at will. In super resolution, I cannot.
So that's my question. So they are different things.
They're very different. They're both instances of undersample data problems, heavily undersample data problems. But in the compressed sensing case, I have the freedom to sample where I want. Right? So I can go in K-space. In fact, that's what these radiologists do. In radiologists, they sample in K-space by using trajectories, they go in spiral, they sample, they design spiral to sample in K-space wherever they want by just creating these magnets, these gradient fields. The fact that we have a physical imaging device, a camera, makes going out of this impossible because of the aperture. And so in super resolution, you're limited by the physics. I mean, you both also, of course, in compressed sensing, you cannot go in K-space at infinity, of course, in MR. But I mean,
So the super resolution will be limited by the physical limitation.